Hello all, let us continue with neural network hyperparameters, and in today's session we will talk about the next hyperparameter, which is different optimization algorithms. So far we have talked about these hyperparameters, and these are the hyperparameters that we will be discussing in next sessions. Coming to the optimization algorithms, these are the most popularly used gradient descent based optimizers. The first is momentum, second AdaGrad, RMS prop, and ADAM. Let us have a quick recap of stochastic gradient descent algorithm and also discuss few of its drawbacks. Stochastic gradient descent is an optimization method, iterative optimization method, which will minimize the loss function by updating the parameters, that is by updating weights and biases. Coming to the drawbacks, the first drawback associated with SGD is it is sensitive to the learning rate, because the choice of learning rate plays an important role in any of the gradient descent based algorithms. The learning rate should neither be too large nor too small. If it is too large, then it leads to overshoot, and if it is too small, then it leads to slow convergence. Coming to the second drawback, convergence speed. Hope you remember the stochastic gradient updation weight graph. It had in this way zigzag direction. This is nothing but noisy data, and due to this noise, stochastic gradient descent is updating weights more in the vertical direction than in the horizontal direction. Generally, it should move from this point to this point, that is move in the horizontal direction, but it is concentrating wasting its time more in the vertical direction than in the horizontal direction, which leads to slow convergence. Coming to the third drawback, inefficiency in high dimensional spaces. So far we have discussed this type of graphs where updation of weights are done by taking the step size so that it reaches the minimum value of cost function. But when we have a complex data where the updation of weights or the data set is in this way, then it has, this is local minima, this is the local minima, this is local minima, and this is global minima. We have discussed what local and global minima is. When the updation of weights is carried out and it reaches this local minima value, here the slope will be equal to 0 because of this plateau, and at this point the machine stops learning, thinking that it has reached the minimum value. But this results in high loss because our minima point of our data set is this one. So due to this, it will have an inefficiency in the operation of the model. Thereby the training of the entire model will stop. So these are the three drawbacks associated with stochastic gradient descent, and to avoid these drawbacks we will introduce few optimizers which will overcome all these three drawbacks. In this animation you can see that this ball gets stuck in the local minima value because it does not have speed to reach the global minima, and this will result in huge loss, which is one of the drawbacks. So to avoid this drawback, what will I do is consider this red point to be as a rolling ball. I will introduce movement into this ball so that it attains high speed, crosses this local minima and reaches the global minima. So making use of stochastic gradient descent with momentum will avoid this drawback of getting stuck in the local minima value. How is it that possible? Let us talk about different graphs which we will be discussing. This is the two-dimensional graph, this is three-dimensional graph, and this is the top view of this three-dimensional graph, which is called as the contour plot. I can say this contour plot as two-dimensional projection of 3D surface. And in stochastic gradient descent, you have zigzag movement of weight updation to reach the minimum value. When I introduce momentum, then it will concentrate more on the horizontal direction, less in the vertical direction. Thereby, the curve gets more smooth, reducing the noise in stochastic gradient descent. That we will discuss. But before talking about the momentum in stochastic gradient descent, let us talk about the exponentially weighted moving average, which is considered as base for all the 4 algorithms that we will be discussing. The first is momentum, second is ADAGRAD, third is RMS Pro, and the fourth is ADAM. The base for all these 4 algorithms or optimizers is exponentially weighted moving average. Now, what is exponentially weighted moving average? It is commonly used as a smoothing technique in time series. For example, you have a complex data like this. So, to have a smooth of this data or this complex data, I will find the exponentially weighted average of all these points so that I'll get a smooth curve. Earlier the curve was something like this. To get a smoother curve, I will find out the exponentially weighted moving average of all the data points. So I can say that it is a method which will find the smooth value in time series. Due to several computational advantages like fast and low memory cost, EWMA is behind the scenes of many of these optimization algorithms. And how do we calculate this exponentially moving average is using this equation. Vt is the current moving average. Vt minus 1 is the previous moving average. This is the current observation. Beta is called as the decaying factor whose value ranges between 0 and 1. This is an example. Initial velocity or initial moving average is equal to 0. So V1 will be equal to beta into previous of 1 is 0 plus 1 minus beta into T1. So this is the exponentially moving average of the current observation taking previous into consideration. Similarly, V2 will be beta into V1 plus 1 minus beta into theta 2 and so on. And this is the generalized equation. And what do you notice here? We can see that for the current value, for the current observation, the weight is 1. For the next it is beta, beta square and so on. That is exponentially decaying. 1, beta, beta square. These are the values which are exponentially decaying. More weightage is given to the current value, current observation, and less weightage will be given to the previous observations and more less to the more previous observations. And general value for beta in all the algorithms what we take is 0.9. You can see here this is an example where a graph represents moving exponentially weighted moving average. The red line graph represents the exponentially moving average of all theta 1, theta 2, theta 3 which are the blue dots, and red points represents what? Higher weightage will be given to the current and less weightage will be given to the previous values. This is the generalized equation of exponentially weighted moving average. Now, why do we take 0.9? You can see here that this is for 0.9, this is 0.6 and this is 0.95. Comparing all these three, the better result is found with beta is equal to 0.9. So, when beta is 0.9, Vt value will be 0.9 into Vt minus 1 plus 0.1 into theta t. The current value is multiplied by 0.1 which is less, and the previous value will be multiplied by 0.9 which is more. That is, more weightage is given to the previous value. Therefore, it tries to move in the direction where the previous value was moving. Instead of moving in this direction, it tries to move in the direction where the previous value was moving. That is, more weightage will be given to the previous and less weightage will be given to the current data point. The best beta value, what I said, is 0.9. So 1 by 1 minus beta is 10. What does 0.9 beta represents? That we will be considering the previous 10 data points to calculate the exponentially weighted moving average. These are different values of beta and their corresponding t values, that is 1 by 1 minus beta. When I take beta as 0.5, I will consider only previous 2 points. If 0.6, I will consider previous 2.5 points and so on. The most general value of beta in almost all the algorithms which has better results is beta is equal to 0.9. Here is a numerical example. These are the theta 1, theta 2 values, and these are the exponentially weighted values using this equation of this graph. And you can see the previously you had more complex data points, blue colored points, and smooth series of values are found using the exponentially weighted moving average. So how do we use this to implement in momentum? This is the equation of weight updation and bias updation in gradient descent. I will replace these two with VDW and VDB, where VDW and VDB are the exponentially weighted averages of these gradients of cost with respect to weight and gradient of cost with respect to bias respectively. So when I have a zigzag value of updation of weights, these are the points which I will consider and find the moving average of these zigzag points so that I will get a smoother curve using that equation what we have discussed in the previous slide. So when I introduce momentum, you can see here that earlier it was concentrating more on the horizontal vertical direction than in the horizontal. When I introduce momentum, it takes higher weightage of the present value, previous value compared to the present value, and blue color line represents a smoother curve compared to the red color line in the given graph here. And what you notice here is it is concentrating more on the horizontal line and less on the vertical line. So these are the three different graphs. This is for mini batch gradient descent. Red color represents for stochastic gradient descent and black color represents introducing momentum in SGD. This is the optimization. This is SGD and SGD with momentum. And what do you notice here? Previously, the ball got stuck in local minima. But as I am introducing momentum, that is velocity, it has gained more velocity that it will cross the local minima and reach the global minima. But what do you notice here is one of the disadvantage here is it is not settling directly in the global minima. After few oscillations it is settling. That can be considered to be as one of the disadvantage. You can see here in the animation also. Here stochastic gradient descent and this ball represents adding momentum. But with few oscillations it is settling down in the global minima value. This is the other animation. So this can be considered to be as the one of the disadvantage of introducing momentum. That is, problem with momentum is oscillations. So we can avoid these oscillations in stochastic gradient descent using second type of optimizer called as ADAGRAD, which is adaptive gradient descent algorithm. So in the previous algorithm so far what we have discussed, we talked about learning rate, which we have taken it as 0.001 and sometimes 0.01 also. This learning rate will be constant throughout the operation of the model. We will not vary this learning rate. So what do we do in ADAGRAD is we will adapt the gradient by different values of learning rates. Because when you are selecting the step size based on the learning rate, for example 0.1, this is 8, the next step size will be difference of 8 which is 7.09 and so on, and this will be the minima value. Depending upon the step size you will be deciding the next step and direction. But in momentum what you had oscillations and then it is settling at the minimum value. That oscillations can be avoided by varying values of eta here. Gradient descent and other conventional optimization techniques use a fixed learning rate throughout the duration of training. However, this uniform learning rate might not be the best option for all parameters, which could cause problems with convergence. Some parameters might need more frequent updates to hasten the convergence, while others might need small changes to prevent the overshooting. So this is the algorithm which makes use of variable learning rates. This was the previous formula what we use. W nu is equal to W old minus eta times of dou L by dou W. In ADAGRAD, we will use this equation. W nu is equal to W old minus eta dash of dou L by dou W T minus 1, where this eta T dash, which is the new learning rate, is old learning rate divided by square root of alpha T plus epsilon, where alpha T is nothing but what? Sum of square of all the gradients, and epsilon is small positive number. It is somewhere around 10 to the power of minus 8, which is used in the denominator, because when alpha T value is very small, then eta minus 0 is not possible. So to avoid the number divided by 0, we will introduce a small constant value epsilon here. So this is the equation what we will be using in ADAGRAD, where different learning rates will be used depending upon the different cost functions. As we are considering all the gradients here in this equation, it tells in which direction to move and what should be the next step size. So this is the graph for the optimization with adaptive gradient descent. More horizontal concentration in updation of the weights than compared to that of the momentum. But you have a problem associated here with ADAGRAD also. When the loss function is increasing, obviously your alpha t value also increases. When this loss is increasing, obviously alpha t also increases. When alpha t increases, as it is inversely proportional, eta t reduces. When eta t is reducing, then there will be no change. That is, when it is very small, Wt will be equal to Wt minus 1. That is, the current wait time and previous wait time values are same. So this will be the problem which will be associated when I use ADAGRAD also. So the solution to this is RMS prop, that is root mean square propagation. Instead of taking square value, we will find the root mean square of loss function that we will discuss in the next session. Thank you all.